Hello, everyone. I hope that you can hear me well. Kostis, can you please confirm?
Yes, Theodore, I can hear you clearly.
Perfect. Okay. So hello again. My name is Theodore. I would like to welcome you to one more Connection Wednesday webinar, our regular online meeting for Idea Statica. This is for us, it's a great opportunity to show some of our customer projects and on top of that also some practical information, some technical information about projects and issues that we have received through our help desk. So together with Kostis, our support manager, who is going to do most of the presentation, we have prepared some interesting material. And for any of you who hasn't used GoToWebinar before, just some basic information. So on the right side of your screen, you can see a control panel, and of course the microphones are muted by default. So if you have any question, feel free to send it through the chat box, through the questions tab. We will try to answer them as we go along during the webinar. We will probably have some time at the end. If not, you can always, of course, send us your questions through email. So just to give you an overview of what we are going to see today. So as always, we have two parts. The first part has to do with a customer project. And today we are really happy to present a very interesting project from an iconic building in London, the Battersea Power Station, that was given to us by AED, our customer in Scotland. And on the second part, we have the help desk example. And today we have chosen to show you how Idea Statica accounts for multiple shear planes in bolded plates. So just to give you a bit of information about the project. So AED is a Scottish engineering design specialist with offices in Edinburgh and Bath, and has become one of the first independent consultancies to use Idea Statica and to exploit its advantages. Of course, they have used it in numerous projects since then, including the one that we're going to show today, which is definitely by far the most iconic one. And this project is the Battersea Power Station redevelopment in London. Just a few bits of information about this project. This building, the power station, has been shut down since many years, and since a few years ago, a new complete redevelopment has begun. Not only for the building, but for the whole area surrounding the building. This is actually, the building itself is actually the largest brick building in Europe. And overall, this project, this regeneration project, is one of the largest in Europe. It costed around £9 billion. And to give you a perspective of this amount, this is more or less the cost of the Olympic Games 2012 in London. So quite a big project. It involves residential, hotel, leisure, and retail spaces, and it will add about 4,000 new homes at this area in the southwest of London. It will be also Apple's new headquarters in London. So today we have a project coming from this site, which has to do with a base plate connection. So AED, together with its client Icon Fabrications, have been tasked by the Robert Baird Group to create to design a high-level temporary roadway that you can see in this picture, which is capable of carrying heavy construction traffic. So once this is done, once the site connection is finished, the structural beams and the columns that you see in this picture will be encased in concrete, and flats will be built on top of this deck. So basically the columns, the steel columns that you see, will be encased in concrete, and these will be the columns of the actual building that will be built afterwards. So it's quite a demanding project, and it also has a lot of interesting information, interesting facts about it. So this is the connection that we're going to focus. We'll show you how we can model it. It is a bit tricky. So we are going to do a lot of, you're going to see a lot of manual, let's say, operations, simply because of its complexity. So the interesting thing about this connection is that it has been designed with mainly two things in mind. First, that it should incorporate the rebars for the concrete column that will be added later. So as you can see, the rebars are going through the base plate and the connection overall. And in the second phase, these diagonals will be removed. And the third part, the third phase, is the concrete column that will cover this steel column and the connection itself. So quite interesting and tricky project. So let's switch to Kosti's screen so that he can show exactly how we can model this complex connection. So Kostis, I'm gonna switch to your screen now. And I think you're good to go.
Okay, so Theodore, just to verify that you can hear me and you can see my screen.
Yeah, perfect.
Okay, so before we proceed with the modeling, let's take a look at the original model that you can see here. So let's have a closer look. And you can see that we have a stub and another stub here. We have two plates, two end plates, and a gusset is bolted on this end plate. And the reason is that the diagonal with the gusset, all this part here, are removed later on, so that part of this connection remains in place and it is encased in concrete. You can also see here that in the model we have incorporated the openings that let the reinforcement bars to pass through the steel element. So today we will model this side of the connection due to time constraints, and the other part is similar to this. So let me close this project and let's move to a new one where I will start from scratch and show you how to model this connection. First, I will add the members. I will start with a column and use a universal column. Let's rotate it so that it is vertical. Rename it. And then add the diagonal. Again, rename it and change its cross section to a circular hollow cross section. and of course add some inclination. Now that the members are in place, I will start adding operations, and first I will define the base plate. Let's use some M24 8.8 anchor bolts. Look from the top, set the thickness of the base plate to 40 mils, and then define the dimensions of this plate. Switch the view to transparent so that I can see the position of my anchor bolts. I will position them in plan view. The bolt rows are there. Now let's position the bolt columns. Again, change the view to solid and see that the anchor bolts are almost there. I will change my welds to full penetration butt welds. Have a look from the side and then change the anchoring length 350 mils and then the anchor type to have a rectangular washer plate. Another thing that's important is to define the shear force transfer method. In this case, anchors resist the shear force transfer. And let's add some mortar of 25 mils thickness. Last, let's define the geometry of the foundation pad. We will use a uniform offset around the base plate of 500 mils, and the plate is there. The next step is to model the stub, and I will use a new stiffening plate operation. Let's rename it to stub. But instead of using a regular cross section, I will add a new welded one. This will be 470 mils high. The flange thickness will be 10 mils thick, and the width will be 140 mils. For the web, we'll have 15 mils. And now that our stiffening plate section is defined, let's modify its size and move it in place. Now I will weld this stub to the column by using a cut operation. So I'm cutting my stub with the column. Let's define the welds to be double fillets and then define the throat thickness of these welds. Now I have to cut the bottom flange of my stub. Again, I will use a cut operation. So I'm cutting my stub, but this time I'm using a plate and I'm using the surface cutting method. If I switch my view to transparent, there are no yellow lines connecting this flange with the base plate. So I need to manually define a weld for it later on. Again, back to the solid view. And now let's add the openings for the reinforcement. I will use an opening operation. I will apply it at the top flange of my stub. It will be a notch applied at both sides. It will be 100 mils long, 35 mils deep. You can see the notches, and I will copy and apply them at the bottom flange. Now let's weld the stub to the base plate. I will use a cut-off plate operation, and I will modify my stub web using the base plate. Again, this will create a double fillet of 4.2 mils throat thickness. Next, I will weld this flange to the base plate, and for this operation I will use a weld operation, which will be an edge to edge. Change the view to transparent. The first plate will be the bottom flange of the stub. It is the edges are numbered, so I want to weld edge number 6 and plate edge number 1. And you can see a yellow line here, which means that this weld is created. Next step is the creation of the first end plate. I'm using the stiffening plate operation and rename it to EP1 for end plate 1. Let's change the view to transparent again, because it is somewhere there. The plate is somewhere there. Let's define its thickness and the geometry. Let's have a look from the side. Rotate the plate, and then move the plate in place. Our plate is where it's supposed to be, and I will use a cut operation to weld this end plate to my stub. I'm selecting plate, and I will use the mouse cursor to pick it from the screen, and you can see that the welds are created. Let's create double fillets, and again modify throat thickness. Then I will copy the previous end plate, rename it to EP2, and I will position it in relation to the previous created plate, EP1. I will position it as a doubler and remove the welds that the software creates, and the plate perfectly is in position. Now I will define the stiffening plates of the gusset. Again, with a stiffening plate operation, I will rename it to TF for top flange. This will be 10 mils thick. Let's define the geometry of this plate in relation to my EP2 plate. And let's set the geometry and, of course, the length, throat thickness. Now let's move it in place. So we'll move it 230 mils to the top. And now I have to create the bottom stiffening plate, which has a bended shape. So we'll use a stiffening member, but for this stiffening member, I will use a new cross section This cross section has two legs. I will use an inclination of 135 degrees. I will set the thickness to 10 mils and then set the leg lengths. The stiffening member is inserted in the model, and now I have to position it in relation to my second end plate, which is EP2. So it will be a rib. Let's use the rear and the other web. Let's modify the welds. Double. Let's modify the lengths of the member, and of course we have to move it in place. Our stiffening plate is there, so I just need to define my gusset. This will be again a stiffening plate in relation to the second end plate. Again, this will be a rib at the rear, rotated by 90 degrees. And now let's modify its thickness to 15 mils and the widths. And then assign double fillet welds with a 4.2 throat thickness. Then I will cut my gusset with the bended member. So I will create a new cut-off plate. The plate to be modified is my gusset, and I will cut it by my SM2 member using the surface cutting method and creating a double fillet weld of 4.2 mils. Then I have to weld the top stiffening plate to my gusset, and I will use a new cut-off plate operation. Again, the modified item will be my gusset, and it will be modified by this member here. And let's create a weld with a double fillet of 4.2 mils. Okay, so there it is. Now, let's connect the diagonal to the gusset we have just created. We will use the clip operation, and we will connect our diagonal to an existing plate, which will be gusset SP, our gusset SP4. I will switch the view to transparent to fine-tune the geometry of the tank and the cap plate. I will then position my bolts in place. Now that my bolts are in place, I will create a double fillet for the tank, and I have to move my clip along the axis of the member. So let's move it further away. And now I'm going to cut my gusset at, in parallel with the cap plate. Again, I will use a cut-off plate operation. I want to select the modified member, which is the gusset, and this will be cut by another plate, which is this cap plate. The shape of the gusset is modified accordingly. The software creates a weld, so I'm deactivating it, and I'm adding an offset of 10 mils. I will change my view to solid and move the clip at the rear so that it's visible from this view. Let's rotate it a little bit, and now I will add a rib. I will use the stiffening plate operation again, and the rib will be defined in relation to the tongue. Let's pick the tongue. Now let's define the geometry of this tongue and a double fillet with its throat thickness. Now let's create another cut-off plate operation to weld this rib with the cap plate. Setting a double fillet, and the model is almost ready. The last step is to add the bolts of the two end plates. I will change the bolt size to M20s. Let's have a look from this side at the transparent view so that I can modify my model. I will use absolute coordinates. And now I will create my bolt columns. And our model is ready to be loaded. I will add a new load effect. Let's add some loading. And we're ready to go. Let's calculate the model and see some results. I would also like to highlight that I have slightly modified the model because I want to show you some failures. The original model was passing all checks, of course. So what I wanted to show you is that when the solution is over, we have a graphical representation of the utilization of each part of the model. So we have some parts in gray. This means that these parts are utilized less than 65%. Some parts of the model are in green, which means that they're utilized from 65% up to 95%. We have the orange parts, which are utilized from 95% and up, but still passing checks. And last, we have the red parts that fail to pass the checks. Besides that, we also have the check tab here, where we can have a detailed view of what happens. So I will switch to the strain check and I will go through quickly because we don't have too much time through these tabs here. First, we have the analysis tab, where we can see that the load case we have defined was successfully applied. Then we have the plates tab. Here we have results for all plates in the model. All plates are presented in a table in a tabular format. And when I select one row, the relevant plate is highlighted in the 3D graphical view with an orange outline. The same happens if I select a plate here. The relevant row in the table is highlighted. Besides that, at the bottom, we have an elevation view of the plate, which is useful if you want to isolate plates and show results, like, let's say, the von Mises stresses or the plastic strain distribution. Next, we have the bolts. Again, all bolts are presented in a table. We see the bolt utilization. We can see the bolt forces, the tensile and shear forces. We can see the resistances and the utilizations in tension, shear, and their interactions. When some bolt is selected, at the bottom view, we can see the plate that these bolts are bolting. Again, in the 3D view, we can see it with an orange outline. We can see the bolt numbers, and I can also activate the bolt forces and show the shear forces here and the tensile forces in the 3D view. If I press this plus button, the bolt row is extended, and we can see the detailed checks and the code formulas for each bolt. The same is valid for anchors. I will not go through them in detail because they're similar to bolts. And I will jump to the welds. Again, welds are shown in a table. If I select a table row, the weld is highlighted in the 3D model. Again, at the bottom, I can see the plate this weld is welded to and its position. And of course, I can also see the stress distribution, the plastic stress distribution along the weld. In the table, we can see the values that are required from the Eurocode for the weld calculation, the utilizations, and again, if I press the plus button, the code formulas and the resulting values. For this case that we also have a base plate, we have some checks for the concrete block, again in tabular format. I can extend this and see the formulas here. And at my graphical window below, I can see the concrete check and the detailed stress contours in concrete. And if I zoom in a little bit, I can also see I can see hatched the effective area of my base plate, which is required for the Eurocode calculations. So with this, I conclude this part of the presentation, and I can move back to Theodore.
Okay, thanks, Kostis. We have answered all the questions that we had so far through the chat. Just one quick one that just came in. Is it possible to have different offsets in the concrete block, offsets from the base plate?
Okay, yes, this is possible. Let me go back to the Design tab. This is my concrete block. I will highlight it, click on it, and the software will move at the base plate operation where this is defined. And here I have the offset. I have just provided a single offset value, but I can provide more than one. I can either provide two values, let's say 500 and 100, or I can provide four values like 100 200, 300, and 400. And if I look from the top, I can see that these distances, 200, 100, 400, 300, are shown here. So we can have different offsets, and they influence the calculation of my anchor bolts.
Okay, great. Another one. This one just came in as well. Hi, for this project, have you checked buckling?
No, because we
No,
don't
we
have,
haven't.
due to time constraints, we didn't check buckling, but we have to,
Yeah.
of course. So maybe we can calculate the buckling. I would like
I hope that
to
doesn't take too
stress
much
out.
time.
Yes, I hope I want to stress out that buckling check is strongly. We strongly advise to perform the buckling check, especially in this case where we have compressive forces. Maybe move on and come back when the buckling analysis is over. Don't know.
Yeah, we can do that. Yeah,
Don't have
because we don't have a lot of time, so I think we should move on to the help desk example. Oh, it's finished, so
Okay.
it's good. So we could just
Yes,
say a few words.
we have a really high critical factor here. So if I go to my buckling check, I can see 6 eigenvalues, and we can also display the relevant buckling shapes here.
Okay, good. Let's stick to that. Let's not go deeper because we don't have a lot of time. So let's, Kostis, if you can move on to the help desk example now.
Okay, just let me close this. Okay, give me a minute because I haven't opened this yet. So let's open the help desk item. So this help desk item that I will show you now came to us through our support channels, and the question was that for this plate here, the user realized that for this bolt row, shear forces were quite different than this bolt row. Now let's go and explain why. Before we proceed, let's have a look from the top and see that we have that this inclined member has a really long end plate, and the designer had to provide an additional plate here. So let's move to some slides I have prepared. And if we change this to a transparent view, you will find out that the top bolt has 2 shear planes resisting, while the bottom bolt has 1 shear plane resisting the actions. So the user was confused because in the idea statica calculation, our shear resistance is not presented like the user expects it to be, because here we don't multiply the shear resistance like in worked examples from the SCI or any other example. Instead, we evaluate the acting shears separately in each shear plane. And we compare this with the actual resistance of the bolt. So let me go back to the model. This model is solved. And let me go at the check. Bolts. I will activate the strain check and select, and I will select this end plate here. Again, go to the bolts. Sorry. So let's select bolt 30. I will remove the bolt forces. So this is the end plate we were discussing about. And for bolt number 30, which is which belongs to the outer bolt column, we can clearly see that there is only one shear force evaluated because we have only one shear plane. But if we take a look at bolt number 40, let's slightly move below, then we can see that we have two shear planes, and the shear force is evaluated along both of these shear planes. And this explains the difference. So this is it. I think that we're almost out of time. So Theodore, are there any questions?
No, I think a couple of questions that came in have been answered through the question tab. So I think we're good. So I'm just gonna switch to my screen because we're almost we're almost out of time. So of course, if you have any questions, feel free to send them to us through email. We'll be happy to answer them. So before we close this webinar, I would like to say many thanks to Tim Hetherington, Director of AED, who was kind enough to provide us with this really interesting project and gave us all the information and the background of this connection that we saw today. So to conclude, after the webinar, as always, you will get a short survey. So please fill this so we can have some form of feedback and try to improve as much as we can the webinars. The recording will be available till tomorrow in our website and on YouTube if you want to watch it again. And for any of you who hasn't used Idea Statica so far, you have a trial. We have a trial version for 40 days that you can use, and you can see for yourself all the advantages of this unique technology. And finally, our next Connection Wednesday will be in 12th of June. And in this webinar, we will show the import of a suspension joint from Autodesk Advanced Steel. So this is already uploaded on the website, so you can register for this webinar as well. So again, I would like to thank all of you for participating in our Connection Wednesday webinar, and we certainly hope to see you again soon. Thank you. Bye-bye.
Bye-bye.